his wife and stuff, and he like introduced me to them. Like, oh my gosh, this is so fun. We talked about biomechanics every day.
What kind of food is it?
Like, it's like a 135 prime, but cheaper.
Huh.
So,
I like that.
Like casual prime dining, so people wear like jeans and stuff. Like it's still good.
Huh?
So.
Maybe I'll have to keep it on the radar for date night with the wife.
Yeah. I guys go there. I know, like, I've met so many people from there that go.
Yeah.
It's close.
It is close. Yeah, we live in Giant Springs, so it's not super convenient but nothing super convenient. So yeah, date night we're like one of 3 choices, and it's all fast or terrible food. So we got to come into town. All right. Well, let's get started. A handful of things. One, I have no idea, man. Just looking at the weather, if I were to guess, there's going to be some type of delays or something in school tomorrow or Wednesday. But obviously, I don't get control over that. But yeah, that would be my thought. If anyone else is following and thinking that, just as we as Texans, I want to say we're bad in the ice, but it's like everyone's bad in the ice. There's nothing you can do in the ice. And then yeah, the propensity to just cancel class would be my guess. So I'm sure you will already be doing this, but if you're not, make sure to be following along to whatever Baylor is sending out. They'll send lots of emails. We'll just follow what they say and do. One of the things that I ran into last semester that was a little different, if we have like a late start of some sort, like if you have like a 9 o'clock online class, and then sometimes it can be difficult to get to your 10:10 class. Anyone have? So that was nuts. Like there were a lot of students who were like, I'm having a Zoom class. This was when they started at noon. I think this was last spring. They started at noon. Like campus opened at noon, but lots of students in the 11, whatever 30 class, whatever time that is, were like, I can't get from home to here, and obviously I can't be like, well, come to campus if Baylor's telling you not to come to campus. So I don't know. Email me if you have problems. Again, I don't know what's coming. I'm just forecasting that I wouldn't be shocked if some type of alteration to the schedule with me. In general, if they just cancel a class or something, I'll put up online videos of lecture to kind of allow you to follow along, which if it is Wednesday, would actually be a pretty good day for it, because there's like a lot of like drawing in my notes of like covering curves and showing and doing a lot of things, and so that's a good opportunity, although it would be a little bit missed because typically I'll start the class on Wednesday with okay, like we're going to draw this graph and y'all tell me where we're at on curves and give us a little bit of practice, so we'll miss out on that. Which leads me into just kind of looking ahead. So our first exam is next Wednesday, so a week from Wednesday. On Wednesday of this week, so in a couple days, I will put up some of what I call learning assignments on here. They are basically ways for you to go in and get an idea of how to study for the exams. So they will ask you questions. Hopefully the questions will be challenging in order to make you study and learn them. That's at least the goal of them. The way that they're set up is you can do them as many times as you want in order to get full credit. Again, that's why they're hard, so that it takes you a little bit of time to study. I don't offer a formal review, but in the past and last semester, like all the students were like, yeah, those were more than sufficient in order to tell me, focus where I needed to study, what you were going to ask, and prepare us as we go through. So just use those as your like, okay, here's our beacon of what he's telling us is important in our notes as we go through. We'll briefly talk about those in class on Wednesday as we go. Any questions? Yes. All right, y'all are easy. All right, so today we are going to talk about enzyme kinetics. So to briefly review what we talked about on Friday of last week, and if you have the ability, if you want to go ahead and open up those notes, I'll ask you a couple questions and kind of zoom back. It just makes it easier on me when you give me an answer as we go through. But realistically, we talked about chemical reactions proceed extremely slow. We used our bad example of like an apple to ATP, and that would eventually happen, but would take really slow. Same kind of processes though in our body. It's estimated that the first step in glycolysis would take about 10 years to happen if we didn't have some other way to facilitate that reaction. And we know we facilitate that reaction through Rex. Enzymes, perfect. Yeah, yeah. We facilitate this reaction through enzymes in which we can now have that reaction happen in milliseconds. Again, the kind of concept of like the ability of reactions to speed up would be the equivalent of a normal reaction is me walking, an enzyme facilitated reaction is me going the speed of light. So we are able to kind of really do that, and that's the entire purpose as we go through. One of the concepts that we can think about is like, since we have this ability, and what we're going to focus on a little bit today is how do we regulate this? Because this process doesn't just mean we want to turn it on and let the enzymes run like crazy. And so with that, let's start kind of in, again, a slight bit of review. This isn't stuff that should be too novel, but it's easy to understand, but I think helps us understand enzymes and how they work as we move through. So in whatever, physics/chemistry, you may have heard this theory. I don't know how much they spend time teaching it in undergrad or even high school classes, but it's really easy to understand. Is this concept of we have this collision theory, aka we have two molecules that are floating around in the environment, and when they collide, the opportunity for a reaction to occur takes place. Yeah, super obvious thing, they're just bouncing around. Everyone can like visualize that in their head. I can do a little dance here to show you, but yeah, collision and a reaction occurs. I'll note whether or not this is exactly how it works. It definitely works in some scenarios, but not all, for the people who want to get into the nitty-gritty, but it really helps us understand this concept of this is how reactions occur. Some type of collision must occur. If they collide, and here is one of my favorite words in the world for anyone who's had my class, this idea of sufficient. Sufficient is what it explains so many like wonderful things. You can just use it in all walks of life. I use it to describe so many things because it's like, hey, how was dinner tonight? It was sufficient, honey. And I got in a lot of trouble by my grad class when I used that example, and they were like, you can't, and I'm like, if it's like chicken on top of like salad, like, it's fine. It wasn't like great, but it tasted fine, tasted good. It was perfectly sufficient. Like, but you can't describe your wife cooking as sufficient. And I'm like, I mean, you're probably right, but it's true. But this idea is like, we don't need an obscene amount. We need more than a little, we just need a sufficient amount is such a great word in biology because so many of the processes are that. Like, we just need a perfectly sufficient amount. With this, we can have either bonds broken and or new bonds formed, then we yield our reactant products. Again, a really simple concept. Everyone agree? Things collide, things happen. Good, good. And then again, we can use this concept to like even think about, okay, like if we increase concentration of the substrates, the chances of collisions are greater. That follows as well. So like here's an example of this here. So here's like, maybe this is a water or aqueous solution. We have blue and red, and in those they will kind of go around. And so here is a low concentration example. And so therefore the collisions will not happen very often because there's just not many blue and reds to collide. If we compare here, these are medium concentrations. You'll see blue and red more together because more substrates cause more collisions, which cause more reactions. Again, this isn't rocket science. Here's a whole bunch of them, right? Lots of collisions occur, lots of reactions to occur, and there we go. So high concentrations of reactant lead to high concentrations of products lead to high concentration of reactants. Everyone's like, yeah, enzymes, this is going to be a great exam. I love this. This is so easy and so obvious as we go through. One of the criticisms of this model, though, suggests that, yeah, just because we may have a whole bunch of substrates are in the solution.
Sorry, everything's so loud today. My bad.
It helps I didn't really hear. I heard one ding, but it's not. I just saw your face of like, I want to throw this. I was like, I don't know, maybe she's really mad that there's criticism of this theory here. Which I guess you're not. Good, all right. So yeah, the idea is like, and again, maybe a good example would be that you put so much tea in sugar, like sugar in tea, that like the sugar, there's going to be plenty of reactions, but nothing will happen. I don't know if that's a saturation problem, but this kind of concept is, it's like you can get it into solution, you can put enough tea in. We're in Texas, right? Everyone's familiar with making sweet tea. I see like lost faces, like making sure, it's like, oh, it's just cold and I don't want to be here on Monday. Peyton, you can't smile at that comment, but yeah, that is true. Like, but yeah. So like this concept though is like in biology we could increase like in that first step in glycolysis, right? Again, y'all have all forgot it at least once, but hopefully we know the first step is just taking glucose and putting a phosphate group on it to keep it in the cell. You may have forgot that. We'll remind you later on in the semester, but that's step number one. And it's really just you get glucose into the cell. Well, like in order to speed up glycolysis, if we didn't have enzymes, we couldn't just chug a whole bunch of Gatorade, get more glucose there, and that's not going to cause more collisions in our cell and cause glycolysis to move any faster, right? So why is that? Like why do we potentially have that? And so this is not my word, but it's a word that I think works, is what we call unfruitful collisions. I would use insufficient collisions because I like the word sufficient, but unfruitful is really the way that you'll see this theory kind of talked about as we go through. So when we say these collisions, ultimately one of the things to note is, in this scenario, is that most collisions are what we call unfruitful. So if you didn't get it, we'll define unfruitful is that most collisions don't result in products being formed. So most collisions don't result in products being formed. Bouncing around, they collide, and then they keep going about their way. They didn't create or destroy a bond, nothing happened, just we had a collision and nothing happened. Again, we'll define that as unfruitful collisions. This is a stupidly heavy chair. Sorry. It's just, like I picked it up expecting to work. All right, I want to hear from you guys. Why do we think that most collisions are unfruitful? What determines if we can think about it in new ways, like what determines if a collision is fruitful, or what causes it? Anthony?
Whenever they collide.
Antonio, sorry.
No, you're fine. Whenever they collide, they don't have enough energy to get over the activation energy.
All right, so perfect answer and using perfect words that we learned on Friday. So one of the things that we talked about is that for a reaction to occur, they all require an activation energy. They all require the input of energy into the system for the reaction to occur. So most collisions are unfruitful. Number one is because there's not enough energy of activation energy. Number one, because there's not enough energy of activation. And again, if you got your notes, or if you can just mentally picture, right, we had that like big hump that we had to get over, even for something that had a negative delta G and something that produced energy, we still had to have an input of energy as we go through. And so with that, like if we just have things bouncing around, you know, we can think about this from a non-biological standpoint, but just a way to think about this is we can do things like increase the energy going on in this. So one way that we can get more fruitful collisions is we can add energy. For example, in our aqueous solution, in our sugar and tea example, we can heat the water. Right? Heating the water makes particles move around faster, makes them collide with more energy because they're moving faster, and when they collide with more energy, then guess what? Then the reaction proceeds, aka we get more tea or more sugar in solution in the tea. Yeah. There's a second reason. Can anyone think about what the second reason of why, not just energy of activation, but there's a second process that must be required in order for a fruitful reaction to happen? Jonathan?
Could be orientation.
Perfect. Man, you guys are on the ball on a Monday. Exactly right. So we have to think about, so he used the word orientation. I think that's a good word. I don't know if that's the word I would use. I think it's actually better than the word I was going to use, is the molecules have to be oriented exactly right when they collide. I'm going to use that. Must be oriented in the right way when the molecules collide. Oriented in the same or in the right direction when they collide. Which again makes enzymes the perfect scenario because they do two things. One, they lower that activation of energy as we talked about, and two, they orient. They have them where they fit them in an exact orientation for the reaction to occur. And so to kind of summarize and finish up this collision theory, again on this side of the graph, it says the concentration isn't always sufficient if the activation energy isn't high enough. So for example, this would tell you that the number of particles, as you increase them, you get more and more collisions, but the actual number of, in this case, fruitful, so this light blue is unfruitful, here's collisions where the reaction proceeds, is still relatively small. If we use enzymes, again, still lots of collisions happening that are unfruitful, but this activation of energy is lower. We've increased some more of the curve, and now these all have enough energy, because the activation energy is lower, for the reaction to occur. And so the study of this, understanding the rate of the reaction, is termed enzyme kinetics, and can be studied looking at different concentrations of reactants in enzymes and how the amount of products are formed. And that brings us to the Michaelis-Menten plot. So Michaelis-Menten plot is how we study enzyme kinetics. For those of you who are taking notes, we're going to talk about a lot on one slide. So conserve or figure out this slide we're going to spend a whole bunch of time on, just making sure we understand what we're looking at on this graph. So just giving you a warning, there's going to be a lot of notes been taken on this graph or on this slide as we go through. So plan accordingly. All right. So the first thing that I do, especially with undergrads, is like when we start looking at graphs and figures, like the first thing I do is like, okay, like in order to understand this graph, first, let's very elementarily break down what this graph is telling us. Like look at all the components, what the graph is telling us and what the graph isn't telling us. So let's do that by starting on what are our axes. So the reaction velocity is on the y-axis. So here you can look at it in one of three ways. I'll give you three definitions. We call it the rate of the reaction. You can also think about it as the speed of the reaction. Rate or the speed. The velocity of the reaction. So the y-axis is one of three things. However, in your brain, it helps you to think about it, whether that's in the rate of the reaction, probably the least one by undergrad. That one doesn't line up as most. Many people can assume speed. So speed is the one that I think pops into most undergrads' head to say, yeah, I get that concept as we go through. Or velocity, which is the exact same thing and the more appropriate science term. Whatever it helps in your brain to think about it. So again, without worrying about what's on the x-axis right now, we can just say that the speed or velocity here is very low. As we go up, so as we follow this graph, like the speed or velocity of the reaction is getting high, and here's where the speed or velocity of the reaction is highest. Really simple things, but again, breaking it down to understand that as we go through. On the x-axis is substrate concentration. So the x-axis is the substrate concentration, which is how much substrate is provided for the reaction to occur. How much substrate is provided for the reaction to occur. And again, to make this on the x-axis, what we do is we add a very small concentration of substrate and measure the velocity. We then add a slightly larger amount of substrate and then measure the velocity. You just slowly increase the amount of substrate available in a solution and then measure the velocity of a reaction. It makes perfect sense as we go through. The one thing that is not listed to make sure that is there is what's known as a fixed variable. So in all of these instances, the enzyme concentration is fixed. So we put in a known amount of enzyme and then measure all of this moving forward. Again, students like to think in like absolute terms, so it's like we put in 100 enzymes and then put in like 1 molecule of substrate and then 5, and then 10, and then 20, and then 30, and then 50. That's not exactly how it works, but it's good enough to understand that that's how we're doing, and then we're measuring when we put in that product, then how fast are the reactants being made by a known or given amount of enzyme concentration. So we can think about it just sequentially adding. The next thing that we'll see is almost all enzymes follow this exact pattern. So enzyme kinetics, almost all of them, and everything that we will talk about in this class, follows this exact pattern. There is a second pattern, which I'll briefly draw, and we'll see a little bit later in the class. But it looks exactly the same. It just has a little tail, so this is a sigmoidal curve. But all for the class and for our approach, it's almost always going to be this type of reaction as we go through. All right, so now that we understand what's in the x and y axis, what can we learn from this? Well, one, we can apply our collision theory here, right? We can say that it's very easy at low concentrations of substrates, the reaction is slowest. Very easy, very obvious. Contrasting at very high concentrations of substrates, the reaction is fastest. Again, we can visualize this. Reminder though that this is not the substrate just colliding and a reaction occurring. This is substrates now colliding with the enzyme and then the reaction occurring. So before we talked about the collision theory as just like molecules floating around like sweet tea to make sweet tea, but here we're talking about the same thing has to happen. These substrates have to bounce around until they are grabbed by the enzyme, until they fit into that, to use the words that we learned last week, the induced fit, until they fit, and then the reaction can proceed. So the collision theory isn't just for molecules at random, it is also they must randomly collide with enzymes in order for this to happen. And the reason that the enzymes then speed up the reaction is one, they make the energy less, so you don't have to have such force in the collision, but two, they also orient them in the right way. And so we can kind of take that, that's what we can take, so low substrate concentrations, lower reaction velocity versus high. The next thing that we can see is almost everyone will reach a maximal velocity, right? So because of this, we will always read, and try not to use too many calculus terms, but we'll reach this asymptote, whereas the line becomes basically flat. We plateau at the end. I have to make sure that I don't miss anything. Slightly different shape. Okay, the last 2 points that we can take from this is that there is always, as I mentioned, there is always a maximal rate of a reaction for a given amount of enzymes. Again, we could cheat, we could add more enzymes, and would that speed up the reaction? Absolutely, but that's not what this graph does. So just highlighting. So there is always a maximal rate, and that maximal rate does tell us one thing, is that even though it may be in order of milliseconds, every reaction by an enzyme takes some amount of time. So just to make sure we're on the same page, like one of the things that we kind of think about and forget, and I want to highlight this because it does important. This is like, again, we talked about the collision theory of things bouncing around in water. They collide, the reaction occurs basically instantaneously. Is that how everyone views it? Just making sure I'm on the same page. Like, two things bounce around, does it really take any time for that to happen? In my brain, I would say my brain doesn't go there, it's just boom, like, yep, happened, instantaneous. In an enzyme, we have to think about what has to happen, right? We have to have a collision with that enzyme. That enzyme has to undergo a conformational change. We have to have that induced fit of it, so there has to be some movement. We have to then undergo a transition state that's somewhere in the middle before we have it, and then we must release the product. Right? And granted, if we were to watch this in real time, that would be really, really, really fast. But to highlight each step of a reaction takes a small amount of time. And we see that here, right? I can increase the substrates as much as I want, and here tells us that that is the maximal rate at which an enzyme can process the reaction. We're no longer limited by how many collisions we have with the enzyme. We're now limited by how fast the enzyme can catalyze that reaction. So that definition is something called the Vmax. So a handful of things to note, and we'll add to our notes here. So Vmax is defined as the maximal velocity. I'll write a whole bunch of them. Okay, let's work our way through. Looks like most people have at least the majority of the notes written down, and we'll run through them as they are. So if you haven't, just focus on when we get to that line right now. So when we look at Vmax, so Vmax again defined as the maximal velocity. It is of course identified on the graph of where the plateau occurs in the curve. So Vmax is identified where the plateau occurs. If that wasn't already obvious, Vmax occurs where the plateau in the curve occurs. In this case, it says the enzyme is saturated. So the enzyme is saturated. Another way to think about this, to add to our concept of the notes, is that we are no longer limited by the number of collisions. So the enzyme is saturated means we are no longer limited by the number of collisions. No longer limited by the number of collisions. AKA, after a product is released, another reactant is immediately available to collide, right? Like we're here, down here, maybe we have, one molecule of substrate and 10 enzymes, and we have to wait until that molecule binds, and that may take time. Here, we're no longer limited by that. As soon as a product is formed, another collision will occur, and the enzyme will proceed. So it is saturated. In this case, the Vmax of an enzyme cannot be increased. There's no way to increase the concentration or the speed of this reaction. The only way we can increase the speed would be to add more enzyme. If we did that, would our Vmax go up? Of course. We have more enzyme available, more ability to do it. We could also look at the reverse. On Wednesday, assuming either in class or online, we'll look at how do things go up or down? How do we regulate enzymes? How do we change the shape of these curves based on changing these kind of concepts as we go through? All right, so the Vmax is the plateau. It tells us that that is the maximal rate of the velocity of that reaction to proceed with a given amount of enzyme. The next thing that we can calculate is what's known as the half Vmax. Maybe you saw something similar to this whenever we talked about whenever in exercise physiology, you might have talked about muscle force and how fast it can contract, and we looked at half contraction time. Cardiac, they look at a lot of half relaxation time. How long does it take for it? And you didn't realize it at the time, but all they were doing was doing Michaelis-Menten kinetics. They didn't talk about it in that way, but that was the concept of to reach, like, how fast can you contract is all done by an enzyme known as myosin ATPase. How fast can you turn that over? And so when they talked about your half relaxation or half contraction time, that is just the enzyme property of it. They just steer away from this because it gets even more confusing and the students don't want to hear about it. Right? So just know this as we go through. But that's how the dots are connected with previous classes. So the half Vmax is calculated just as you might imagine. It is just half of the velocity of maximal. So here's the maximal velocity. These are teaching graphs, so they don't have numbers, but let's say this is 10. Half of that would be 5, and we would calculate the half Vmax. So again, if it wasn't obvious, it's concentration equal to half of the Vmax, and it is defined as the substrate concentration in which half of the enzyme active sites are full. And I will note, half Vmax doesn't tell us that much. But you have to calculate it. So if you aren't obvious, and we'll get to our third one, but if it hasn't become obvious already, you will for sure on exams and on your learning assignments, you will have graphs and you will be told what is the Vmax, what is the half Vmax, and what is the Km. You will have to calculate these for certain on your exams. That wasn't completely obvious of how much time we're going to spend looking at this figure. Hopefully it was obvious. You'll see it in your learning assignments as well. So the last thing is what we look at is we calculate Vmax, then we look at half Vmax, and we drive that calculation and we draw a line. Where it intersects with our velocity or our curve, we label as the Km. So the Km is the location where the half Vmax concentration intersects with the curve. Everyone follow? And I will note, this doesn't jump out to me when I was first learning it. It's like, this seems obviously important. This doesn't jump out to me like, why do I care? Like, most people think, isn't this the important part? Like, isn't Vmax the important fast? Like, how fast can we go? It's like, yeah, that makes sense. And it's like, well, if we think about it in the car world, there are some things where it's like, how fast does this car go? But what most people care about, not just how fast the car goes, but like, how fast can you get that car up and like going really fast, right? That's a better thought. It's like, okay, I can drive this car 300 miles an hour. It's like, great. How long does it take you to get to 300 miles an hour? 2 days. Would anyone want to drive that car? No, right? Like, it would have a massive Vmax, but it would be miserably boring to take that long to get it up and driving. Or if I said, I got a car that'll go 0 to 60 in less than 3 seconds. Oh, for the car people, like, yeah, that's a fast car. I'm intrigued in that. And the really awesome, expensive, and stupidly cool cars, the cars that do both, right? That can go really fast and can get up and go really fast as a combination. And so what we kind of think about is that is the important part of what many people think. So in our analogy, like a car that gets up and goes, in theory, is more important. And that's what our Km tells us. Like, how fast can we increase the rate of reactions? So the Michaelis-Menten is the concentration where Vmax occurs. And it allows us to compare a new word for the day, and a very, very important word to understand as we move through this class is affinity. So Km allows us to compare affinity between enzymes. So highlight affinity, we're going to give you examples, we're going to talk about it here in a little bit, but that's our kind of key word is Km tells us the affinity of the substrate to that enzyme.
Is there always a one-to-one ratio between the percentage of Vmax and the percentage of the enzyme active sites that are full? It's like at 1/2 Vmax, half the active sites are full, so is that always like a one-to-one?
Yes. But what it can tell us, and I'll jump ahead, so it's always that one-to-one, but if we think about it, I told you, like, one of the kind of concepts is like, we don't think about it, but that reaction takes time to occur, like binding, conformational change, transition state, product react. What's ultimately what we're looking at is the affinity. How fast does that happen? How fast does it create? And how fast does it spit it out? That's what this graph tells us and doesn't become super apparent. Because most people don't think, oh yeah, there's amount of time for all of those little steps to happen. This graph now puts it into context. How fast does that happen? So in the one-to-one, yeah, it is still half of them are occupied or the other half not. Either way you can think about it, glass half empty, glass half full. But yeah, that ratio still exists, but it's how fast can it turn them over? All right, so when we compare Km between reactions, so the Km value is an intrinsic property of the enzyme substrate system. It cannot be changed or altered by changing the substrate or enzyme. So this gets to your question. It's like, does that always exist? Yeah, as long as if I increase the concentration or increase the number of enzymes, my Km actually always stays the same. As we highlighted, Vmax will change, right? Like, I can just add more enzyme and Vmax will change. But Km won't. We can change Vmax by adding more substrate, adding more enzyme, but our Km will be exactly the same. Which, a word that I want to also highlight in your notes here is an intrinsic property. So this is another fancy science word that maybe you don't know, but intrinsic basically means of being oneself. That doesn't tell us much if I was to define that, but being oneself. Here's what that means from a scientific perspective. Intrinsic property is defined, is different for every single enzyme. So every single enzyme has its own curve and its own Km. Every single enzyme has its own curve and own Km. Intrinsic, another better way to think about it, is unique, because again, a being of oneself, it's individual, everything has its own curve and unique. So how can we use this to kind of understand and define, like thinking about this from one? These 2 points are incredibly important, so put a star by them and we'll see them on the graph. So it says when a substrate concentration is less than Km, changes in substrate concentration will greatly affect the reaction rate. To add to your notes on that point, to just say, like, basically if we think about this, if we look at the slope of this line before your Km, so here's our Km, to the left of our Km, so we can write before or to the left of the Km, the slope is really, really high. So to the left or before Km, slope of the line is high. And so if I go from a concentration of here, so let's say a concentration of 1 to a concentration of 3, again just making up numbers, but it illustrates it, we went from here to here on the reaction velocity, right? So a large slope means small changes in concentration, large changes in velocity.
Does that mean slope is 1/2 that Km?
So that means slope.
Yeah, does that mean like the slope of the line is 1/2, like a 45-degree angle where it intersects with Km?
I guess define what you're kind of asking for to make sure.
Slope be like 1/2 of the line.
No. So, because just jumping ahead to kind of show, like, as you can see, slope, this kind of changes. So there's an example, there's 2 examples.
But wouldn't Vmax also change with those? Like I'm saying, like the intersection of Vmax and Km. Or 1/2 Vmax, rather.
Oh, yes. So this is always how we find it. So draw this 45-degree. Yes.
Okay.
Okay. I didn't know if you were getting into the calculus of,
Yeah,
of
yeah,
this.
that's what I mean, like at that intersection. Like, I
Yes.
feel like the slope should be 1/2 there, but I'm not sure.
I guess when you say by slope, do you mean
Like the slope of
like the integral? So integral, are you calculating integrals? Because this is
That
not,
would
this is
be
a,
derivative.
this is a curve of linear line, so it doesn't have a,
That would be derivative.
or sorry, derivative, yeah, yeah. So we don't have a
Like the slope
slope.
the slope of the tangent line.
Yes,
Yeah.
through derivative.
Yeah.
I don't know.
Okay.
Good question.
I feel like it should be, but just
Yeah.
thinking about it.
Yeah, I'll have to do the math. Like, oh, calculus, I forgot all about derivatives. Yeah, because like we don't, again, it's not a good word to use slope here because this is a curvilinear line.
Yeah, I meant the tangent line.
But yeah. But again, steep, and then if we compare to the opposite. So on the opposite side, on the right side of Km, at concentrations that exceed or are greater than, so exceeding to the right, the reaction rate increases much more slowly. Again, to just kind of jump back, we're out here. If we go from a increase from here to here, our rate is very slow. And so this ultimately determines our rate of reactions. If we are low concentrations on this side of the Km, the reaction will increase really, really fast at slow changes. On the other side, very, very slow. All right, so let's take a look at what is affinity. So I'll note this is not a perfect example. This is not a perfect example. Hemoglobin, if you are to Google it, it's actually what they call it someone Google it, like a wannabe enzyme. It's not really an enzyme, an honorary enzyme or something. It's like, but it's an example that we can use from something that y'all learned in previous classes, whether that's physiology or exercise physiology or both. We can kind of look at this graph and understand these as we go. So let's quickly just look at the oxyhemoglobin curve. Again, this is our sigmoidal curve, but if we just kind of ignore down here for now, we can just kind of focus. This is exactly what our graph looked like previously, right? As a side note, just to connect the physiology, this is something that I'll quiz you on, the hemoglobin physiology, but just to like remember what makes hemoglobin such a cool and unique protein is that when you look at it up here at concentrations at high or medium, concentrations of oxygen have to get actually pretty low before the oxygen saturation in your blood goes down. And so we can kind of look at hemoglobin saturation. If we want to connect it to the lecture today, we could be like the velocity at which oxygen binds to hemoglobin. Not a perfect analogy, but really good for connecting dots in physiology. And again, at room temperature, so at room air, we're roughly at about 105 millimeters of mercury for the partial pressure of oxygen. So if y'all were to put a little pulse ox on, anybody do this in class? And you put a little pulse ox on, you should be like 99 to 100%. And the good news is, like, if oxygen concentration decreases, let's say you have a disease where maybe you have COPD or something where you can't get a lot of oxygen in, a large percent of those patients never have any problems because they can still keep the partial pressure of oxygen in their lungs above like 50, which means that their oxygen stays plenty saturated. Above 80 to 85 is usually considered, they'll be healthy and not really have any problems. And so that's what makes it really, really special, is that all we're doing is sitting out here on the Km, but what makes it cool is how steep this slope is. And we can say that basically once you get here, so what makes it cool is that low partial pressure of oxygen, it will release. So partial pressure of oxygen in muscle is about 20, and it will then, the velocity of the reaction of it binding will not occur. It's not a perfect analogy, but oxygen will be released into muscle. And so we take it to the lungs where partial pressure is high, it grabs oxygen, takes it to tissues where partial pressure is low, and it releases oxygen, which is really cool. Again, which makes it not a true enzyme. It's got shapes of enzymes, but it's really, really pretty cool. Another word to kind of go back and use the words that we just previously learned is this concept of affinity, right? So here we have a high affinity of oxygen, and here we have a low affinity of oxygen. With that concept that like affinity is how much is being bound. And so we can kind of look at this to come back to kind of more abstract examples, and we'll go back to the hemoglobin example here in just a second. to contrast affinity as we go. But I like to introduce that because I think everyone's brain can connect with that affinity from hemoglobin. Is that a reasonable thought? Everyone's like, yeah, I remember they may even use that word. High affinity, low affinity, high affinity in the lungs, low affinity and low partial pressure. These are really cool. So affinity is defined as the capability of recognizing the specific substrate or how strongly the enzyme binds with the substrate. So these two concepts are why we have to teach. In the last lecture we highlighted the lock and key and why it was insufficient to explain that is because the Km, which is our measure of affinity, that induced fit, understanding that, how, recognizing a specific substrate, right? Two Legos didn't look like they fit, if we remember our notes from Friday. And it's like, okay, they could fit, they would induce, and then when they do, how strongly do they bind in order to kind of create that reaction to occur? You need a strong binding in order for transition state, all of those things to occur. And so because of that, that induced fit is how we get this understanding of affinity of enzymes, is that, yeah, the enzyme kind of changes its shape in order to determine its affinity. So when we look at affinity, we typically talk about it in two ways. We talk about either a low or high. So as we kind of look, we can draw these graphs here. So one thing that we can say about these two curves, to break this down, is that the Vmax of these two curves is equal. Everyone follow there? So our red line, one enzyme here, one enzyme here, when we increase substrate, ultimately when we saturate them, the maximal velocity of both of these enzymes is the same. Vmax is equal. If we take half of our Vmax, so I'm just going to kind of make something up, but we'll say, let's say roughly right about here. Kind of do this in your notes. It doesn't have to be perfect. We're just comparing these two, and then I draw my line for our 45 degrees. Here, our 45 degrees for our black line, our Km is roughly, I have it labeled here, G. So here is our Km. Everyone follow? We can do the same thing for the red. Note, it'll come across at exactly the same line because our Vmax is the same. And our red Km is here. All right, here's where things are in my kind of concept backwards, at least after writing my brain. So we would say the black line has a low Km. So black line has a low Km and therefore a high affinity. Low Km represents a high affinity. So our black line, a low Km and a high affinity. Again, in my brain, I always have to reverse it. Still to this day, I want to think high Km means high affinity and high speed of reaction, but it's the other way. Low Km, high affinity, high rate of reaction. Low Km, high affinity, high rate of reaction. And the red line then, of course, has a higher Km, which represents a lower affinity and a lower rate of reaction. So here's our example of affinity looking here. So again, if we kind of think, here's our Vmax, here's our Km, here's our half Vmax, here's our Km. If we compare it to why carbon monoxide is so deadly. So carbon monoxide, its binding affinity is here. So same Vmax, but now calculate the Km. So again, 150, the Km here is extremely, extremely low. And so therefore we could tell us very small concentrations of carbon monoxide causes a large amount of it to bind to hemoglobin. That's why it's incredibly dangerous. 1 to 3% can actually cause physiological impairments. Very small increases in the partial pressures of carbon monoxide can bind here. It only takes a couple percent to be at its Vmax. And so, and this may be a word that you've heard or thought about, is that carbon monoxide has a high affinity for hemoglobin. And the secondary problem of why it's so deadly is it doesn't have a sigmoidal, it doesn't release either, so it doesn't come off as well. But from a physiology perspective, we know that carbon monoxide has a high affinity, aka a low Km, for hemoglobin compared to oxygen. All right. We'll save this. We'll start off here so that we don't run over time. All right. So on Wednesday, against a alert of your emails, I know you all will, and I'll update whenever Bailey tells us. I'll give y'all update through Canvas, just do an announcement to tell y'all whatever the plan is as we go through if they change for anybody. All right. Stay warm. Stay safe.